Hi everyone, welcome to News Chem Corner. If you are new here, don't forget to subscribe, hit the bell icon for more chemistry smart videos. Today we are going to dive in the final review for chapter 6, Thermodynamics. Let's get into the video. So in this chapter, you see the percentage, it's 7 to 8, 7 to 9 percentage, something more than that, because see the second part of the thermodynamics is also included here. That is in your syllabus, it's given with the chapter 9. Okay. But here we are going to deal that one. So considering that one, it's something above that 7 to 9 percentage. Okay, so in this chapter we want to learn with a thermochemical reaction and the different method of enthalpy calculation. That's all the first chapter, the first part. Stoichiometry, calorimetry, Hess's law, formation enthalpy, bond energy, through different kind of way how to calculate the enthalpy of a reaction. Okay, delta H. And that spontaneity, that's why I told you that is actually the chapter 9. They were including in chapter 9. Okay, so let's do this one. So first one, as I told you, what is thermochemical reaction? Thermal energy involved reactions are what we call thermochemical reaction, which means, as you know, some reactions need thermal energy like heat energy, then only they can convert it to product. But some other reaction, they release heat energy during the reaction. Okay, so the first one is called a endothermic reaction and the second one is called a exothermic reaction. So both endo or exo, the heat involvement is there. So how much heat is involved, right? If involvement is there, then the question is how much heat is involved. So how much heat is involved? Delta H heat is involved. So how much is delta H? That is we are gonna calculate. That is we are gonna calculate here. Okay, and through different method. Delta H is positive, endothermic is positive for the delta H, and delta H is negative for exothermic reaction. Okay, so see, this is the potential energy diagram for exo and endo. Here reactant is started from the lower energy and here product have higher energy, which means energy in total they were added. Energy is added. So it is an endothermic graph. Okay, and here what is the thing? This is the reactant and this is the product. So energy is released. Product at the final position have a lower energy, which means energy is released. So this is an exothermic graph. So final minus initial, energy of final minus initial, this shows the delta H. Okay, and what is this activation energy? Yes, how much energy is needed to get the activated complex, because every reaction you can't see any direct transition like reactant to product, like that direct transition is not there. Every reaction have to take place in this route. They need to pass a high energy unstable position and then only they can convert it to product. So how much energy, how much is the threshold energy they need to get and then to convert the product. Okay, that is what we called activation energy. So the first one, reactant to product, is this one. This is the activation energy. For the second one, also reactant to product. So this is the activation energy. Okay, so that unstable thing is what we called activated complex. Without activated complex, we can't get the product. Okay, so that's the potential energy diagram. And then you will study like what you mean by system and the surrounding. You know, if you are studying, like if you need to calculate the reaction enthalpy for some particular reaction A and B giving C and D, then this reaction, if it's taking place in inside a container, then inside the container is what we called our system, and the surrounding other than the system is what we called surrounding. Okay, so when we talk about endothermic system, like endothermic reaction, the energy is transferred from surrounding to system. Okay, surrounding to system, system is taking the energy. We are always in the point of view of system. Okay, and when we talk about exothermic reaction, system releases energy and who take that energy? Surrounding will take that energy. So for an endothermic reaction, according to surrounding, it's actually exothermic. Okay, so that's why you can write Q system or delta H system is equal to delta H surrounding, but with a negative sign, because one is gaining the energy, the other one is losing the exact same amount of energy. That is first law of thermodynamics. Okay, so delta H or Q is also you can consider like the heat amount. Okay, Q is usually the current scenario, like delta H is always like kilojoule per mole reaction. That's the only difference between the Q and delta H. Okay. For particular amount, some 10 gram you are added. For the 10 gram reaction, maybe we will tell like Q amount of Q is equal to this much. That much of energy is involved. But according to one mole balanced reaction, not one mole, for a one balanced reaction, how much heat energy is involved, that is what we called delta H. Okay. So that's all the difference between the Q and delta H. Okay. Then the thing is how to calculate the enthalpy. So if you delta H is what we called enthalpy of the system. So if you study, if you understand the enthalpy, then how do you calculate the enthalpy of a reaction? So you can use different method. The first method is see stoichiometry. How do you use with the stoichiometry? Stoichiometry is very simple. You are provided with the thermochemical equation like this. Then normal stoichiometry. Suppose see the question, how much energy is produced if 100 grams of hydrogen is converted to water? So you are starting with 100 grams of hydrogen, and then what you need to do is how much energy. So normal stoichiometry, gram you can convert it to mole. Hydrogen is 2.02 gram because it's diatomic, and this is 1 mole of hydrogen. And then what you need to cancel the moles of hydrogen. So see the relationship, 2 mole of hydrogen, one balanced reaction contain 2 mole of hydrogen, but the energy is minus 571.7 kilojoule. So that's why I told you delta H unit is kilojoule per mole reaction. Per mole reaction means for one balanced reaction. That's the meaning. Okay. So here one balanced reaction involved 2 mole of hydrogen. So you have to relate 2 mole of hydrogen with the minus 571.7 kilojoule. Okay. Want to take that 2. It's not 1. Okay. This is not kilojoule per mole. Everything is per mole. No. It's always delta H also always for mole reaction, per mole reaction. Okay. So consider the 2 mole at the bottom and the corresponding 2 mole corresponding energy is minus 571.7. So that should be the answer. Okay. In this way, normal stoichiometry question, through the normal stoichiometry you can calculate the delta H or the normal Q. So this time this is actually what you find is Q, because for this particular reaction you are calculated how much heat energy is involved. That's I told you the difference between the Q and H. Usually H we are telling there is not that kind of difference actually, but in your syllabus, according to the syllabus, usually we are representing the Q is for current scenario and the delta H is for the one balanced chemical reaction. Okay. So that's it. So the all this is just like a enthalpy of a reaction. So stoichiometry is that one, and then you can do with the calorimetry. So how do you use with the calorimetry? As you know, calorimetry uses the specific capacity. So in calorimetry you can expect 3 different kind of reactions. So first one, dissolution. They can give you the dissolution values, and then there may be neutralization reactions. Okay. And then there will be hot metal questions will be there. So these are the hot metal is adding to the water. So these are the 3 system of we are doing with the calorimeter. Okay. What are the thing? Dissolution, neutralization, hot metal. Hot metal is really easy. Okay. Anyway, so dissolution means what's the dissolution means? You are adding some salt to the water. So they will dissolve the thing, right? So when they dissolve, how much energy is involved for that dissolution reaction? Is it endothermic or exothermic, or exactly how much reaction is involved? Okay. So for example, see the thing, when a 12 gram of sample KCl is dissolved in 75 grams of water in calorimeter. So temperature drops from 31 to 21.6. Calculate the delta H for the process. So this is the thing. Okay. So here this kind of calorimetric problem, how to do the thing. First one, there is a water. So water is we are considering like a surrounding, and the other one is system. System is what they were given like dissolution of KCl. So KCl is our system. Okay. So yeah, usually this kind of questions, 3 steps are involved. Q water you have to calculate. Q water, how do you calculate? MC delta D. But very careful, while you taking the mass, it should be the combined mass for dissolution reaction. What I'm telling, the mass should be the combined mass. Why? Because the mass is also dissolving. right? For the dissolution, see in this case KCl is dissolving in water. So the mass of water is actually not only the mass of water itself, the KCl dissolved salt mass is also included. So the mass here is combined mass. Very important, only in case of this dissolution reaction. Then hot metal, we didn't take the combined mass. Okay, specific capacity of water and delta T of water. In that way, we are calculating the Q water. So in this case, what is the stuff? Mass is given like 12.8 grams of salt plus 75 grams of water, and the specific capacity is 4.184, and then the temperature difference is final minus initial always. So 21.6 minus 31. So see, the question will be why the temperature decrease has happened. Because the reaction, who took the energy? Why the temperature decrease? Temperature decrease of water means the system took some energy, isn't it? For the dissolution process, they may took some energy. That's why the temperature is decreased. If water temperature is found to be increased, what does it mean? So the reaction releases some energy. So the first point you can understand from this one, this reaction, KCl dissolution reaction, is an endothermic reaction. Why? Because water temperature, what is the surrounding temperature is lost means, yes, system took the energy. So endothermic reaction. Okay. So definitely you got some Q, negative Q water, right? Okay, definitely it should be a negative quantity, whatever it is, it's just X. Okay, and then second step involved, how do you calculate with a Q system, right? So now in KCl, in terms of KCl, how much heat is involved? So again, you don't want to calculate the MC delta T mass of KCl times C of KCl delta T of KCl. No, we are already calculated the surrounding temperature, right? This much of energy, water lost this much of energy, which means system gained that much of energy. So Q system is nothing but negative of Q water. Okay, so negative of Q water. So what is Q water we got? That's X quantity. Okay, definitely it is negative X. So now it is a positive quantity. Okay, so I'm just taking minus X means actually it is a positive quantity, right? Because this X itself is a negative quantity. If minus 5 is X, then the Q system is plus 5. Okay, so that's the second step. And third step, there is also a third step. Third step means, yes, delta H. We need the delta H of this reaction. So as I told you, delta H means for a one balanced chemical reaction. What we found, Q system we found, but that is only for this 12.8 grams of salt. So now what we need, the one balanced reaction contain 1 mole of KCl. So for 1 mole, how much it is? So you can just multiply with their molar mass of KCl. So in that way you can calculate the energy. Okay, so three steps are involved. First you are calculating the Q water. Second, you need to calculate the Q system by just changing the sign, and the third step, delta H, by doing the stoichiometry. Okay, so what we found is only for 12.8 gram. Then what it is for 1 mole. Okay, that is how we need to calculate the calorimetry with a dissolution reaction. Main thing, mass is not that water mass alone. This is the combined mass. Okay, then second type of reaction, see this kind of hot metal is there. That's so simple. Like hot metal, you are added to the water. What happened? So a piece of metal weighing, see the mass is this one, and was heated to 100 degrees Celsius. Put it in the water of 100 ml of ml. Initially it was 23.7, and then is thermal equilibrium. They were underwent the thermal equilibrium, right? The temperature will flow until the thermal equilibrium is gained. So what do you mean by thermal equilibrium? Yes, both of them reaching in the same temperature. Okay, so 27.8 is the final temperature of water. It's also the final temperature of metal. Okay, so at that time you can again tell Q system is equal to negative of Q surrounding. So this time Q surrounding means again the water. This time you don't want to consider the combined mass because metal and water will not dissolve, right? So mass of water here 100 ml. So 100 ml is means 100 gram because water density is 1. Then C is 4.184 and the temperature difference is 27.8 minus 23.7. So this is the temperature of water. Okay, and there will be a negative sign, and Q system we don't know, like 59 is the mass of system 4047, times the specific capacity we do not know, and the temperature difference. This time final temperature is 27.8 minus 100. Okay, then you can solve it for C metal. That kind of normal calorimetric question will also be there. Okay, that's it. And the third kind of question is neutralization reaction. See the thing? Neutralization reaction is something like this. NaOH 100 ml, NaOH is added to the 100 ml 1 molar HCl. Both are mixing. Both solutions are originally at 24 degrees Celsius. Okay. After the reaction, final temperature is this one. So here both are, you are adding to the calorimeter. So inside the calorimeter, before mixing, there is nothing. Okay, first you are added some 100 ml of NaOH is there, and then you are added 100 ml of HCl. Okay, then after that one, initially both are at the temperature 24.6. Now the final temperature is 31.3. Okay, so how do you calculate? Like neutralization reaction. Okay, what do you mean by neutralization? Yes, NaOH reacting with the HCl. This is the neutralization reaction. So for this reaction, how much energy is involved? Delta H for this reaction. This is already balanced. Okay, this is delta H is involved. Like delta H is what? Okay, so again you can use the Q is equal to MC delta T. We are calculating the what is the thing? Surrounding Q water. MC delta T. So here mass is what? Yes, definitely the combined mass, right? There is 100 ml NaOH and 100 ml HCl. So totally 200 ml solution is there. The same ml solution is same. Specific capacity is 4.184 like that. You can take, and that see the density is also 1 gram per centimeter. Okay. So you can consider yes 100 grams of solvent is there, like water is there, and the specific capacity is 4.184. And see the temperature difference. What was the temperature difference? 31.3 minus 24.31.3 minus 24.6 is the final temperature minus initial. Okay, so this is what? This is Q water. Then what about Q system? Yes, you need to take the negative of Q water, the second step, isn't it? And then third step is just stoichiometry, right? If you know the Q water, this is for how many things? This, see the thing, 100 ml 1 molar solution you have took, isn't it? Both of them is 100 ml 1 molar. So what is the number of moles? What is the number of mole? 100 ml 1 molar means, what is the number of moles? Number of moles is equal to molarity times volume. So 1 times volume is 0.1. So here 0.1 is number of moles. So this system energy is actually 0.1 molar reaction, 0.1 molar NaOH or 0.1 molar HCl. So here no limiting reagent, or both of them is limiting reagent. If suppose the one is 0.2 and this other one is 0.1, you have to go with a limiting reagent, 0.1. Okay. So Q system, like what I am telling is delta H. Delta H is what that's for 1 mole of reaction. So what you got is Q negative of Q water is what? 4.1 mole. If limiting reagent involved, write the limiting reagent number of moles. Okay, this is for 1 mole. So see, when you divide it with a 0.1 molar, you got it per mole. So that is all about the delta H. Okay, this kind of calorimetric question also can be there. Okay, trace heating up. Now you can see the question. So how much heat energy is required for raising temperature of 80 gram water minus 20 to 120? So here can we do Q is equal to MC delta T, like mass is 18 grams, specific capacity is 4.184, and delta T is 120 is final temperature minus initial temperature is 20. Like that, can we do like this? Absolutely no, right? Because this water heating, see, it's involved in different phase changes. So C is equal to M for is 4.184. 4.184 is only applied for liquid water. If it is a solid water, definitely that is not the value. Okay, got it? So minus 20 to 0 means solid water is involved. So at that time you can't use 4.184. And also that's the one reason. And also there will be some stages. where delta T is 0. Correct? In when you are heating minus 20 to 120, there will be some states are there, like where temperature change is not there. Even though you are adding some heat energy, see the heating curve. The heating curve, like the temperature while you are adding the temperature change, sorry, heat while you are adding, the temperature change is not a continuous manner. Okay, so see, minus 20 to 0 they will continuously change or continuously increase. After that, for some time temperature is not changed. Okay, temperature is not changed. Why? Even though you are providing the heat energy, why there is no temperature change? Yes, because of the phase transition, right? Here at 0 degrees Celsius, solid is turning to liquid. So some energy is used for that phase transition. So due to that one, here there is no temperature change. So you can't use MC delta T. MC delta T you can use only when there is a temperature change. Okay. So this slanting position you need some another like you this horizontal position you need some another equation. Okay. Anyway, after 0 they will change to 100. It's a continuous change, and 100 again there is a phase transition. So uh, they will stay the constant. They will stand the constant. They will stay the same temperature, and then it will increase to what some 120 or something. Okay, in this figure it's maybe more than 120. Anyway, that's the thing. Got it? So it's stage by stage, it's different. So what you need to do is, for the all slanting position, like the sloped position, you can use the equation Q is equal to MC delta T. If temperature change is there, you can use Q is equal to MC delta T, but be careful while choosing the value C, because C is different position. They have, like solid they have one value, liquid they have another value, and gas they have another value. Okay, and then horizontal portion you can use the number of moles times the latent heat. Latent heat means how much energy is needed for the phase transition. For example, latent heat of fusion means how much energy is needed for the fusion, solid to liquid. Okay, and similarly, latent heat of vaporization means how much energy is needed for changing to liquid to gas per mole. Okay, so that's the thing. So in that way you can directly use the equation. I think you are okay with that concept. And then the next law, so that's all about the calorimetry. So we done this stoichiometry, calorimetry, and next one is Hess's law. Hess's law, as you know, there will be a set of reaction, and you need to calculate another reactions delta H. Okay, so what to do is, you need to bring this unknown reaction, this reaction, from this set of reaction. Correct? Okay, for that you maybe need to do some manipulations. Delta H is also manipulated in that way. Okay, for example, if you want to bring this Fe2O3, C3 you need, which equation involved the Fe2O3? Which equation? The first equation involved the Fe2O3. So we can take the equation 1 multiplied by 3, because you need 3 Fe2O3. Okay, you need to bring 3 Fe2O3 in our equation. So you can multiply with the 3. So 9CO will be there, and 6 Fe will be there, and 9 CO2 will be there. Okay, so your delta H is also manipulated like that. So delta H is also multiplied. Here you are multiplying. So delta H is also multiplying by 3. Then CO you want to bring. So which equation contains CO? There will be a confusion. Like both equation contain CO. So you can't manipulate in correct way. So you just keep it. CO2. CO2, see CO2 is also contained, like both equation involve CO2. So at that time just skip CO2 also, because then only we can do the correct manipulation. Okay. Then what about the next one? 2Fe3O4 as a product. Yes, only one equation contain Fe3O4 as a product. Okay, like in on Fe3O4 it's only in one reaction, and we need as product. So this equation is already in product, and 2Fe3O4 you need. Okay, so we can multiply with the equation 2 times 2. So that will be bring 6 Fe plus 8 CO2 gives 2 Fe3O4 plus 8 CO. Okay, so delta H is also multiplied by 2. So if you reverse the reaction, delta H is also reversed. If you add the reaction, delta H is also added. Okay, so yeah, so that will bring us same changes like what same change like a same equation like this. Okay, so the reaction we got, but we need like 3Fe2O3 plus CO gives CO2, isn't it? Because see, here 9 CO and here 8 CO, so it's cancelled and 1 CO remained. Here 8 CO2 and here 9 CO2, so 1 CO2 remained at the product side, and yeah, 6Fe will cancel. So we got the equation we required. And the delta H will be, see, I'm just writing, this is delta H1, this is delta H2, and we got delta, just add delta H1 plus delta H2. Okay, that's all about the Hess's law, H1 plus delta H2. Okay, and then in the equation we are calculating the what formation enthalpy thing. So if they were given with the formation enthalpy, how to do it? So you can use this equation. Formation enthalpy, if they were provided the formation enthalpy of each compound, then you can use this equation. What is the equation? Sum of formation enthalpies of product minus sum of formation enthalpies of reactant. So this is the reaction, and they were given the delta H for the reaction is minus 430. So minus 430 is given, is equal to this is not per mole reaction. Okay, so formation enthalpy of CH4 is given. Formation enthalpy of CCl4 is given. CCl4 is question. Formation enthalpy of HCl is given. Okay, what is formation enthalpy of Cl2? Every element in their native form, formation enthalpy is 0. Okay, so this one is 0. So what's the equation? Product minus sum of product. So here products are CCl4. So formation enthalpy of CCl4 plus formation enthalpy of HCl. So HCl, what is the formation enthalpy? Minus 92.8, but that is 4 in number, so have to multiply with the 4. This is the total formation enthalpies of product minus the sum of formation enthalpies of reactant. So reactant CH4 is minus 74.9. Okay, then plus only one thing, and 4 times 0. As I told you, chlorine, the formation enthalpy is 0. Okay, every element in the native state it is 0. So make sure this kind of like calculation thing, minus and minus, so those kind of things you may do have to care. Okay, otherwise maybe mistake will happen. So just solve it for this value. Okay, so that is all about the formation enthalpy. If they were given with the formation enthalpy, this is the thing you need to do. Then the question is, what is formation enthalpy? So for example, what is this one? The equation for standard enthalpy of formation of N2O3. Formation enthalpy itself, what is the meaning? Okay, so formation enthalpy of something meaning, so suppose in case N2O3, the meaning is that have to form from their own constituent element. Okay, so N2O3 is composed of their own constituent elements, which means nitrogen in their native form, which is N2, and oxygen in their native form, which is O2. Okay, then how do you balance this one? While you balancing, this is 2, maybe like you need to do here, so that will make a 4, and how many 6, so this will make a 3 here. But actually two conditions are there for formation enthalpy. First one, it should be from the constituent element, so which is N2 and O2. And second thing, you need to make this one is constant 1. This one should be the coefficient should be 1, because it's always formation enthalpy is always for per mole. So in order to make this one is 1, yeah, this equation is divided by 1 half, divided by 2. Okay, multiplied by half. So 3 over 2, like that it will come. So energy related to this reaction is what we call the formation enthalpy of N2O3. So which is the option? See, N2O is involved, definitely no, this is a compound. N2O5 is again a compound, not possible. NO is again a compound, yeah, N2 and O2, those are element. And see, they will make sure the coefficient of N2O3 is 1. So the D option will be the correct one. Okay. And the last method is bond energy. How do you calculate from the bond energy? Delta H is, suppose they were given the bond energy, bond dissociation enthalpy. How do you calculate? So this is the equation. Delta H is equal to formation, sum of bond broken minus sum of bond formed. Okay. So what do you mean by that one? See, for this one you need to draw the Lewis structure actually. So HS is this one, O2 is this one, double bond O is actually plus H2O means this is the, sorry, gives H2O means this is the thing. Okay, and see how many bonds have to break. A reactant bond, see this is reactant minus product, actually not reactant minus bond but reactant side you have to look first. Okay, because reactant bond have to break and the formed bonds are these things. Okay, product bonds. So how do you make the equation? Here how many hydrogen bond you need to break? See, two H2s are there, right? So two hydrogen bond have to break. So 2 times 436 plus 1 time O2. So O double bond O. So they were given O single bond O, but that is not the thing we need to use, right? We need double bond O. Do they given? No, that is the question. In this case, that is the question. Okay. So anyway, there is one X bond, like one O double bond O. So we can consider like X is equal to, sorry, minus, this is the bond broken minus sum of bond formed. How many bonds you need to form? Yes, OH bond is formed, 2 OH bond. Is that 2? 2 for 1 H2O. So there are 2 H2O molecules, so 4 OH bonds are there. Very important. H2O usually you took just 2. No, there is 2 OH bond in 1 H2O molecule. So there are totally 4 H2O, 4 OH bonds are there. So each one is 464. 464 moles of energy. Joules of energy is involved. Kilojoules. Okay. So this is the equation, and that is they were already given minus 240 kilojoule. If it's O, what is this? O double bond O bond. That is the question. Okay. So we can expect this kind of questions. Then thermochemistry part 2, like you are dealing in with the chapter 9, like as a electrochemistry, but this is actually the second part of thermochemistry, spontaneity of the reaction. So spontaneity, two factors are affecting the spontaneity, delta H and delta S. This is the equation, delta G is equal to delta H minus T delta S. Delta G means the gives free energy. What does it mean? They just, it's a combined effect of entropy and enthalpy. Okay, entropy is, the disorderness, how much disorderness is there in the system. Okay, higher the disorderness, entropy is higher. So every system is like highly chaotic, highly disordered, entropy increasing, that is their favorability. And delta H, they have to be exothermic. Both favorable means delta H have to be exothermic and delta S should be positive. Okay. And what about the delta G? At that time, delta G will be negative. So delta G negative is what we called spontaneous reaction. The reaction will do themselves. We do not want to do anything. The reaction itself will do, the system itself will do that reaction. Okay. So if someone is asking like thermodynamically favorable, which means spontaneous reaction, delta G is negative. One more point. For thermodynamically, even though thermodynamically favorable, which doesn't say the speed of the reaction. Some reactions are very slow reactions, but they are thermodynamically favorable. Those kind of reactions are called a kinetic controlled reaction. Okay, so what do you mean by kinetic controlled reaction? Their speed is very low, but they are favorable. Okay, so some kind of question be like that. So in kinetic controlled reaction, you can get a very active, very high activation energy. Okay, so you can expect that in the question. Okay, right. And in this part, what is on we need to know is this chart. Okay, so what should be the delta H, delta S? You can easily study if both are negative, negative like low. Both are negative at low temperature, it is spontaneous. If both are positive, high temperature, it will be spontaneous. Okay, one is positive, one is negative, which means you just think about the conceptual thing. A system is always want to increase the entropy, so that the opposite, negative, like an exothermic reaction. This is the system thing. So they like to do that one. So that's why spontaneous at all temperature. At the same time, if both factors is disfavorable, then definitely that is endothermic. Endothermic and entropy decreasing reaction. So that will lead a non-spontaneous reaction at all temperature. Okay, right. Then see, how do you do this kind of question? Molar heat of vaporization is given, molar heat of vaporization, which means for 1 mole of water, if you want to vaporize means H2O, liquid to gas. For this transition, so latent heat of vaporization is given 43.9 kilojoules. What is the entropy change? Delta S is they were asking. This is delta H and delta S is they were asking. So how do you calculate? Delta H and delta S, you know only that the one equation, right? Delta G connecting equation. Delta G is equal to delta H minus T delta S. But the problem is, what is delta G? Do they given? No. See, what is delta G? For equilibrium or for all phase transition. All phase transition reactions are equilibrium. Like equilibrium, they were having equilibrium steps. So if equilibrium is involved, definitely delta G is 0. Or phase transition, delta G is 0. Okay. So delta, at that time you can consider delta H is equal to T delta S. So that, yes, delta H is given 43.9 and the temperature is what? Water vaporization temperature means 100 degrees Celsius. So 373. So divided by 373 will be the delta S. Okay. So in that way you can calculate. And make sure this is kilojoule, and always delta H value should be in kilojoule and delta S is a small quantity, so that should be in joule. Okay. So that kind of calculation you can do it. Clear? Yeah, so that's all about the chapter 6, the whole review, the checklist. I hope you understood all. And if you have any doubt, you just comment below. And yeah, share, subscribe for more videos. Thank you.